So one has the idea that there is a spherical object. And I'm going to start off with making this thing constant density. And it's going to be pressure, so that I can calculations. And I think that we are deducing that means that the objects making up this stuff move along geodesics. If we didn't do that, the energy momentum tensor TAB for such materials is rho UA UB, where this is the 4 velocity. And then conservation of energy momentum, del A of TAB, that must be equal to 0. That's the same thing as del A of rho UA UB. That's the same thing as UB of del A rho UA plus UA rho del A UB. This is 0 by the equation of continuity. And this is the same as the geodesic equation. So that thing has got to be equal to 0. So the particles that make up this collapsing cloud will move along geodesics, and so you have this vague idea that they will all sort of go inward, something like this. Now the metric outside, we said, had got to be exactly the Schwarzschild metric, because outside the collapsing body you are spherically symmetric. This thing is, that means that if you satisfy the vacuum field equations you must be static, and so you know you're going to get the Schwarzschild metric. The exterior, so we know that the metric is going to be given by a familiar looking expression. Now to make life easy for ourselves, let's suppose that this collapsing matter has total mass m, and that it starts collapsing when its size, meaning that in the Schwarzschild metric R is equal to big R. Another way of saying it is that that means that its surface area is 4 pi big R squared. This does not mean that its radius is big R, because you don't know what the metric is inside here, at least not yet. And initially it's at rest. Since a particle on the surface will see either the interior metric or the exterior metric, it doesn't really matter which, because the metric is supposed to be smooth as you go from here to here, you may as well say that particles on the surface will follow geodesics in the Schwarzschild metric. We don't know what the metric is in here yet. So all you have to do is to integrate up the geodesic equations in the Schwarzschild metric. Well, we can all do that. It's the same calculation that we've been doing recently. And if you go back to the equation that we have up there, you can sort of see that one way of writing this would be to say that, well, obviously they move radially inwards. So theta dot equals phi dot is equal to 0. You're only
because you can have some going on.
What would pick out the direction?
No, but if you initially have that, it's like a random, the particles are initially in random motion.
I said that I was going to start at rest. You want to put motion in, you can do it, but it will be much harder. You might have something on your mind that I can tell you about. Well, actually, I'll tell you now. So you might be saying, well, suppose the thing was rotating. How do you know that the thing actually undergoes gravitational collapse as opposed to the centrifugal force keeping it up? Is that the question?
No, I was thinking more of it as a type of gas or something.
It would have pressure, wouldn't it? If you have, let's say, two superimposed spheres that are rotating in opposite directions, so you've got a whole bunch of stuff going in one direction, the other one going the other direction, so you have no net angular momentum. Then you have a pressure, don't you?
There would certainly be pressure if, well, there would be a layer where, presumably there was a layer where the two things met.
So it wouldn't satisfy her. I mean, we're looking at something that's pressureless.
Yeah, it's true, but I think you might be able to do it without pressure too. This is an idealization. I don't think you need to worry about it. If a real gas, if it's cold enough, you don't have to worry about it. No, I can't remember what I was trying to do. So what's going to happen here? I start off with a gas at constant density, and it undergoes gravitational collapse. So we have a situation that looks like this. And then the interior is made of something. And we are interested in the pressure-free thing. So as a first guess, you might imagine that if it starts off with constant density in space, it stays with constant density in space. Somewhat amazingly, you know some solutions that do that to the Einstein equations corresponding to pressure-free matter. So, solutions to the Einstein equations with pressure-free matter and constant spatial density. If I rephrased that and called that being homogeneous and isotropic, you'd all immediately know what I was talking about.
Flat FRW matter damage.
Sorry?
Flat FRW with matter damage.
Flat FRW. Well, it is FRW that is matter dominated, pressure-free stuff, but it doesn't have to be flat. So these are things that you usually think of as being cosmological models, but they don't have to be. Let me write down the metric of such things. And then the spatial part of the metric can be anything you like, as long as it's got constant curvature. To make this work, you have to choose to have closed Friedmann-Robertson-Walker models. So the metric looks like that, where chi runs from 0 to pi. Now, how do I know that that actually is the right thing to have done? Well, there's a choice of three possibilities: flat, open, or closed, parameterized by k, and I obviously chose k equals plus 1. And there's a very obvious clue as to why that works. If you ask what are the solutions of the Einstein equations which correspond to this metric, you know that the answer is A of eta is equal to half AM, in other words, the maximum size of the universe, into 1 plus cos of eta. And you know that if you were going to calculate, wait a minute, I should call that E, call that T. Tau as a function of eta is a half AM into sine of eta plus eta. So those give you the equation of the expansion factor. Now, of course, you will see what the trick is. These equations are the same as these equations. So, in other words, as a result of a miraculous coincidence, the scale of the Friedmann-Robertson-Walker universe obeys exactly the same equation as the surface of this collapsing body. So that is a hint that you can actually manage to match up the space-time metrics. So inside, you can have the Friedmann-Robertson-Walker universe. You want to think of the analog of the radial coordinate as being chi. Well, you've got to match up the metric on this surface to the Schwarzschild metric. How do you do that? Well, this is a surface of R as a function of eta. So what you can do is you can take the Schwarzschild metric, substitute in for R and eta, and you'll end up with some 3 metric describing this surface for all time. So if you do that, you will discover the induced metric on the surface R of the star, is going to be ds squared is equal to. Well, the easiest way to do this is to call this R of eta into d omega 2 all squared, because you just had an R squared in front of that, minus some function squared of d eta squared. And to find that metric, what you're going to have to do is to differentiate t and r as functions of eta and substitute it into here. I do not wish to do that calculation. You could do that calculation. You can certainly imagine doing it. We've written down t as a function of eta and r as a function of eta, and you will end up with some formula that will look like that. But I can tell you the answer. The answer is for fixed chi, so in other words, you just put chi equal to a constant here, with r is equal to a m sine of chi 0, and m is a half a m of sine cubed chi 0. So in other words, inside this sphere, the space-time is metrically the same as part of a closed Friedmann-Robertson-Walker universe out to chi 0, or at least part of it, and outside the collapsing body is exactly Schwarzschild. I recommend that you try doing this calculation, but it is an incredible mess. As a warning. So the result is that you now know what the interior metric looks like. It looks like the Friedmann-Robertson-Walker universe. But one thing you know about that is that as you shrink it down to 0, you see what's happening is you've got a Friedmann-Robertson-Walker universe that is collapsing, as opposed to expanding, so it will collapse down to a point. That will be singular. So at the final stages of collapse, you see, you have a Friedmann-Robertson-Walker universe of 0 size, you know that to be singular, and Schwarzschild outside it. If you want to do more detailed calculations, you will have to use a computer to do it. I don't want to do that. This is one that works in a nice, relatively nice, easy way, analytically. All computer models of collapse will produce roughly similar pictures. And the only difficulty is if you have too much angular momentum when the calculations become rather confusing. I don't want to contemplate angular momentum at the moment. What then does the space-time look like? The easiest way is to think about constructing a Penrose diagram for this metric. Now, it starts off as being absolutely non-singular with nothing strange going on at all. You just have a star which is sitting there that doesn't involve any horizons or anything peculiar. So it's like a blob sitting in the middle of what would otherwise be Minkowski space. Let's suppose that it has always been there. Now, if that's all there was to it and it sat there forever, then what you would do is you'd have a Penrose diagram that looked something like this. So this would be r equals 0, and your star would just sit there forever. So this would be the star, or blob of gas or whatever. So that's what would correspond to an absolutely static star. That's, of course, not quite the same picture as we got here. Here, you know what is happening. In the past, it's got to look something like that, but you know that it is going to collapse to form a singularity, and at late times, you also know that it's got to look like the Schwarzschild metric. So if you think long enough, you will end up with a picture that looks something like this. That won't work too well. So in the remote past, I have something which looks like a star. So this is the line r equals 0 for the star. So the star is basically some ball of stuff that looks something like that. Now let's suppose that at this time I say, all right, I'm going to allow the thing to undergo gravitational collapse. Perhaps that means turning off the pressure or something. What will happen? It will collapse down to form a singularity. So this is the point where the thing has 0 size. So in this region where collapse has started, the space-time will be exactly Friedmann-Robertson-Walker, part of Friedmann-Robertson-Walker. And you will end up at the singularity there. What about outside? Well, it's exactly Schwarzschild. As I've drawn it, you can see that all of the trajectories are moving along time-like lines to form this singularity. But outside the collapsing body, it's exactly Schwarzschild. And you already know how to construct the Penrose diagram for it, and you'll end up with a picture that looks like that. So here, it will be Schwarzschild. Now you can see what the event horizon is. The event horizon is the past light cone defined by the boundary of the past light cone of Scri plus. So it's going to look something like that. That's the horizon. Horizon formation is not a violent process. In fact, in this model of gravitational collapse, you don't see it at all. It just happens when the thing becomes sufficiently compressed. So nothing peculiar happens here, or here, or here, or here, or whatever, when the horizon forms. The only way you're going to find it is by asking when do geodesics that are outgoing and null stop expanding. So this is the kind of situation you expect to find in gravitational collapse. There is a singularity to the future, as there would be in the Schwarzschild metric, but unlike the exact Schwarzschild metric, there is nothing peculiar or strange about the past. So there's only a singularity in the future. So this is the kind of Penrose diagram you expect to find associated with real black holes where they have formed by gravitational collapse. It's quite different to the kind of Penrose diagram that you get if you were going to say that I'm going to look for a metric which has always been Schwarzschild. So there is quite a a noticeable distinction between the two different cases. So that brings us to a question of definition of horizon. I've taken it here that what you mean by horizon is quite obvious. But I want to show you a situation in which the notion of horizon is less obvious. So this introduces the concept of apparent versus event horizons. So I imagine, again, that I'm going to study gravitational collapse. So I'm going to have a star which is collapsing to form some kind of singularity. So let me draw what's regions of space-time that you cannot escape from. Or the boundary. So, if you look back to this picture here, this surface is an apparent horizon. If you are inside it, you're stuck inside it. But you can be here, and you'll definitely be outside it, but still within the event horizon, because you're inside this yellow area. You cannot escape from infinity, sorry, to infinity from here. So it's clear that the apparent horizon does have something to do with curvature of space-time, because it represents a location where the gravitational field is so strong that you can't move outwards.
Does that definition just include your future light cone as well?
Yes and no. I don't wish to discuss that question yet. So this does involve some notion about the local gravitational field. If I may interpret your question, the question is, does an apparent horizon have a future endpoint?
Well, also, it just isn't everything an apparent horizon. You just draw a flat space with nothing in it, and a point, and the future of that point is an apparent horizon.
The future of that point. Let me see if I understand what you're saying. So here is some point. Here is the light cone, future light cone. And what's the issue?
That's also an apparent horizon. You can't escape.
Oh, I see. True. But that's kind of different to this. I've given you a loose definition for the very simple reason that it's very hard to give a precise definition. What I'm aiming for is an idea that somehow light rays here are somehow trapped. But I can't easily give you a definition of trapped. Hence my reticence to produce a more precise answer. See, the trouble is that with many of these things, when you're trying to define something very precise about what you would like to happen in space-time, it's very easy to invent counterexamples. And you discover that some simple things just don't work terribly well. Hawking and Ellis is full of it if you want to try your hand at that kind of thing, but I don't recommend it. The idea, however, is more to produce an intuitive understanding of what's going on rather than to be absolutely mathematically precise. Otherwise we will, let's say, tie ourselves in knots. So that's the difference between an apparent horizon and an event horizon.
Physically, what's the difference? I mean, let's say you're inside the apparent horizon of the inner cone there. Right?
Yeah.
If you're going to feel around, you know that you have an apparent horizon right nearby because you can't move outside of it.
That's right.
Right. But how can you have any physical? How can you do any experiment to verify that there's a bigger horizon around you?
You can't. If you're just sitting here, you would have absolutely no idea. The best that would happen is that if you got on your rocket ship and tried to do something like this, you would discover that you ended up back here in the future. The point is, you just simply can't get past this yellow surface, however hard you try.
Sure, I mean, we're raising
But if you're sitting here,
Yeah.
there's absolutely no experiment that you can do that will tell you about this yellow line.
Yeah. No. I know that. What I mean is that we've raised the status of the yellow line over the white line.
That's right.
Right. So, but if you're inside the white line, if you're inside the apparent horizon there, there's nothing to
Here.
distinguish your status from. I mean, you don't even know the yellow line exists.
You don't know the yellow line exists.
Yeah.
Correct.
So why does it have a higher status?
Because if you were an astronomer sitting at Scry Plus, looking with your telescope, you would not be able to probe this region inside the yellow line.
Mm-hmm. Oh, okay. But it doesn't matter to you if you're in the inside hole.
Well, it will eventually, assuming that most things that I think one pretty much believes are true. Here, you will find yourself in this singularity. But here, you will also find yourself in a singularity. That's because once you've formed an event horizon here, eventually this shell of matter will also collapse. Let me attempt to draw that. So here you have this collapsing shell of matter, and eventually it will do something like this. I suppose.
Maybe two singularities join. Why do they need to join?
Well, assuming that they don't have to join, but assuming that everything was nicely spherically symmetric, they would be the same. It was a. They.
Couldn't you have the singularities twist around each other?
You might be able to do that. If you have spherical symmetry, that won't happen.
No.
And that's what I was thinking of when I drew this picture. If you're here, you will still end up in the singularity. So the answer is, of course, if you waited long enough, you would know. But I think that isn't what you meant. You were asking about, could you do some experiment here, in this region of space-time, to discover the existence of a yellow surface? The answer is no, you cannot. But it would get you in the end.
Can you have inside this event horizon two singularities?
Could I have two singularities? I don't see why not.
Both of them by staying in the middle?
Depends whether they're space-like or time-like.
Sure, they both.
Yeah, but they'll collapse into each other.
They will probably attract. You have to be a bit careful about this.
They have to be
So,
rotating around each other or something. It's got two spiraling singularities.
well, if it's like Rice and Nordstrom, of course, there's no reason why they would have to hit each other. But if they're space-like, then I think something peculiar has got to happen. But if they're time-like, I suppose you could imagine some bizarre scenario. But if they're time-like anyway, you won't necessarily have to bump into them. The content of the singularity theorems tell you that if there is an event horizon, but it really is an event horizon, not an apparent horizon, and the energy conditions are true, then there is a singularity in the future. It doesn't tell you how many or of what type.
Okay.
So I don't see why there shouldn't be more than one, but I find it a little hard to imagine if they're space-like.
Can I ask one other question?
Yeah.
Presumably there's nothing to stop like loads and loads and more shells further out.
Oh no, absolutely not. There could be a lot more outside.
In an event horizon like that, and if you had another shell outside.
Oh well, then it would be wrong. You'd have to go through the whole procedure again.
So the event horizon is like the last shell.
Yes, the outer one.
How do we know
Yeah.
this?
You don't. Well, you just simply don't. You can't. There's no experiment that you can do to check it. It's one of those facts of life.
So we could have a space-time where there is no event horizon, despite there being multiple apparent horizons.
No event horizon.
By having shell after shell after shell.
Oh, you want an infinite number of them.
Well, if you're inside a black hole,
Or you just in
as far as you're concerned as an astronomer, you have no sky plots, right?
Well, that's true. You would be close to it. But if space-time is asymptotically flat, and something is inside its own Schwarzschild radius somewhere, there must be an event horizon.
So if we have asymptotic clamps, then we get away with it.
Yes, but now you're going to ask me some terrible question about non-asymptotically flat spacetimes, and I can't tell you the answer to that. You have to do it yourself. I don't think there's enough time to start what I was going to plan next, so let's stop there.